Okay, good. Here we are. So I have these two formulas up here. We're just going to run through what happened, and then we can spend a little time discussing this thing here. So this was the time average over the energy of the driven damped oscillator. It has natural frequency omega naught, and it's being driven with this omega frequency here. So the differential equation was originally omega naught, sorry, it's more. So the differential equation was two derivatives, two gamma, one derivative, omega naught squared x. And here we had F naught over M cos omega t. And we took a few steps to get through using the complex numbers and so forth. Okay, so we have this thing. And the structure of this, since we'd already studied the amplitude resonance, we can see that for omega equals 0, you're going to have some constant value because you've got that omega naught squared there. Okay, so here's the function of omega, the energy. So you're going to have some constant value. It's going to increase and reach some kind of a maximum. And for very large omega, you can have omega squared here and here, but you're going to have omega to the fourth here. And that tells us that this thing decreases. Okay. And so you've got some kind of resonance peak there. Then we made some approximations. So here, we let gamma for small, gamma, and then omega close to omega naught. We made those approximations, and we got this really nice simplification. And that's right at the end of the hour, so of course we want to spend a moment discussing what we found here. And you know, you'll look in your notes, you'll see we did some stuff like omega naught squared minus omega squared equals omega naught minus omega, omega naught plus omega. And if you're close to omega naught here, this is approximately 2 omega naught. That's how we were able to make those simplifications. And up here we did close omega, therefore we close omega naught, so we call this m omega naught squared and this omega naught squared. So yeah, you get this very nice simplification, and this thing you can just read off what's happening, as opposed to this one where it takes a lot more analysis. So now that we've got the time, let's have a quick look at this. So now we've got the energy time average as a function of the driving frequency, omega. And again, if we take omega equals 0, it simplifies, but it's not the same as what we had here before. We're going to have omega naught squared plus gamma squared. Okay. And also, as omega gets really large, we can see that we're going to have that omega squared behavior that we talked about right here. Right over here, it's 1 over omega squared. So we're going to retain that. But what we're most interested in is the behavior close to omega naught. So we'll just put our omega naught right here. And then we see we have, when omega equals omega naught, we have a well-defined value here. And actually, I'm not going to write the average, I'm going to write what we have here. We're going to have F naught squared over 8m gamma squared. Okay. And that's the peak. Another thing to look at is if gamma is 0, zero, you've got something that diverges. I'll do this in a different color. So if gamma is zero, you would just have 1 over magnitude omega minus omega naught squared. So you'd be looking at something like this. Diverging. And that, of course, would be the resonance catastrophe we had talked about. So in this case here, where gamma is not zero, you're looking at something that is just very symmetric and well behaved. It looks like that. So that's a resonance curve. And if you were driving this system, you've got this machine here, you're cranking up the omega, and you were taking careful data, then the the energy that your system is radiating or displaying is going to increase like that systematically until it's going to have its peak at the resonant frequency and it's going to decay again. So this is a curve that you can experimentally, and this is usually done with driven electric circuits, okay, but this is a very general principle here. You can generate this, and if you record this, you can now figure out the values of these parameters over here. Because you're driving a system you can't actually get your hands on with a ruler, okay? So there's another interesting point here. If you have, okay, so we have the peak here, that's clear. If you have omega naught minus omega squared equals gamma squared. Omega naught minus omega squared equals gamma squared. Then this thing here is exactly 1/2 of its maximum height. Okay? Because if this is gamma squared, then you have gamma squared plus gamma squared, you have 2 gamma squared. So then you would have 1/2 of f naught squared over 8n gamma squared. And let's have a look at this. Suppose omega, we'll switch this around, omega minus omega naught equals plus or minus gamma. Omega equals omega naught plus or minus gamma. So what that is telling us here, I'm going to go over to here. So here we have omega naught plus gamma, here we have omega naught minus gamma. So the width of this peak is equal to 2 gamma. Okay, width of the peak. And since gamma tells you how strongly the oscillator that's not driven is damped, you now have just from this analysis here, if this were a real system, you have from this analysis, you found what this was and you found out what that was. Okay. And actually having found that out, then you could even say what F naught was if you didn't know already. So I'm going to put a note here for you guys about that differential equation. So this is usually done with driven circuits, driven electrical circuits. And the differential equation looks something like L d squared Q dt squared plus R d Q dt plus 1 over C Q equals cos omega t. Anybody recognize that differential equation from physics 4b or somewhere?
I don't know if we ever saw it in this form.
LRC circuit resonance. So forth. Okay. And so this you can actually do in physics 4B or some other lab where you have the circuit elements, you know, you can actually dial all these things in. With a mechanical system, not so easy to realize. So that's where this is realized in a lab. I think that's what I think, right? Inductance, resistance, capacitance, and then you've got a voltage there, driving the voltage. And then it'll often take the next derivative of this and get a current, you know, measuring current or something. If you took one more derivative of the whole thing, you'd have dq dt is I, and so forth. But anyway, if you haven't seen it yet, you'll probably see it at some point. Physics 4B lab does some stuff like this without knowing these differential equations. Okay, good. But here is a mechanics problem. This is a really excellent one. And that pretty much makes up what we were going to do on small oscillations. We'll come back a bit and talk about complex numbers some more and review some of those problems. But what's next on our plate? Any questions on this? How about you? Had you seen the LRC circuit before and the resonance problem? Yeah, exactly. So this is where it can really be realized, and got an oscilloscope and you dial everything in 4 meters. Okay, good. We're moving forward into 2- and 3-dimensional physics now. Remember I told you at the beginning of the semester we're going to spend half the semester almost doing 1 dimension. Now we move into a couple dimensions, 2 to 3, and some interesting stuff coming up there as well. I think we're pretty much on schedule though. The theme always is Newton's law, and we've just been doing so far and T. Look at it that way. Vectors, we've been doing 1 dimension. In fact, we did forces that are simply a function of position, velocity, time. We did all 3 of those. So we're just going to take it into curves in space as opposed to just linear motion. So what we've had until now was 1-dimensional version. T. We did a bunch of these. Actually, we did the 3-dimensional version for constant. So here, just to make this have the correct order, we did do equals constant acceleration. In particular, we did it for gravity, and therefore we got the parabolic motion. We got the projectile motion out of this X and Y launch. So that's an important case. Then we did what I just had written down. X dot and T. We did some individual cases here. Okay. Ending with the particular one that we've just done now is f of x, where you had a potential energy. Okay, so that's kind of the progression of what we've been doing so far. You had a potential energy function. From this, you had conservation of energy. You had the first integral, had the technique of getting the quadrature. And then we added that explicit driving force for one case, or damp-driven oscillations. Okay, so you can see, and it's always good for you to go back and see the progression of the ideas we've been following so far. Okay. So we had that, and then we had 1/2 kx squared, right? And then we got our oscillations. So back into motion in 3 dimensions and pick up a couple more interesting problems. Culminating in the Kepler problem, okay, which will take a little while to get there. So I have as an example, or as the next thing to talk about, is circular motion. At the very beginning, we touched on circular motion a bit. I derived a certain E squared over R. So we want to do circular motion and uniform circular motion. And this is something you get in physics 4A as well, right? Circular motion. So there we're in the plane. Okay, and we're moving on a circle of radius R. Starting with the uniform circular motion, then V is constant equals 2 pi radius divided by T. Here, T is the period of one complete rotation. Okay? If you want to describe this position vector as a function of time, we can have, I'll go ahead and put a capital R for us now. Cos omega t R sin omega t 0. And we'll just drop the 3rd dimension since we know we're in the plane. Okay. But what's this omega here? Well, since we have 2 pi periodicity, we can relate these two right here without any problem. Okay, omega times capital T will be 2 pi as we go around that circle there. Okay, so we can relate it to velocity if we want. Knowing that, we're good just leaving it as omega, okay, angular frequency. So there's your position vector. We're gonna ditch this thing here. Okay, we're gonna ignore this one. Just work with a 2-dimensional vector. And start taking derivatives. So V the magnitude of V. So now we're dealing with vectors. We've got magnitude of that vector would be the square root of omega squared R squared sine squared omega squared I squared cosine squared. So the sine squared cosine squared add up to 1. Okay. So when you do that, you just get omega squared R squared. I'll go ahead and write this in. Sine squared omega t plus cosine squared omega t. Just to have done it. So yeah, so we have this, it's just omega times R. And we got to do one more now. We have to do the acceleration as well. But important to see, I'll go ahead and put this here. You've got minus omega R. You've got this, or not, you've got omega R, sorry, minus sine omega t cos omega t. And these two vectors are perpendicular to each other. And what that means is that as you're moving around counterclockwise, your velocity vector is pointed there. have some space here. Make sure that's good and clear enough. Okay, so once more. Actually, let me get them all together here. So we now have R is equal to R. In fact, it's better if we pull the R out now, but cos omega t sin omega t, right? And now we have V equals omega R minus sin omega t cos omega t. So we've taken those two derivatives. Cos omega t. Okay. And the point that I just made here is that note that R dot V is equal to omega R squared. The dot product is what I'm interested in. I've got a cosine omega t sine omega t. Cos omega t sine omega t. And one of these has a minus sign, this one. Sorry. So I've got minus cos omega t sine omega t plus sine omega t cosine omega t. Okay. So that equals 0, and that tells us that these two vectors are orthogonal, perpendicular to each other. And there's my picture. And what about the acceleration vector? So now we have this nicer form to work with here. So now we'll take dv dt, so acceleration equals dv dt, and we've got the omega r. And when I take the time derivative, I'm going to keep the minus sign and I bring out another omega. Okay. This one I'm going to pick up a minus sign and bring out omega. Right? So when I do that, I get another omega here. And minus sine omega t minus cos omega t. Let's clean that up. We have minus omega squared r. That's backwards, guys. So we took the derivative, we get the minus cos omega t minus sine omega t. Okay. So now, okay, we pull the minus sign out, and we have cos and sine, which is what we had up there. So this is actually, what is that? Minus omega squared r. So where's the direction there? Let's get another color into the mix here. So now, that acceleration vector is actually pointing right back. Origin, and that's the centripetal acceleration.
Okay, so centripetal acceleration now makes sense to me because it never what we did before.
Yeah, second derivative just reverses the direction of that arrow. Okay. So acceleration, that's a very important result. Okay. So we'll call it the centripetal acceleration. Now that comes about when you have uniform circular motion. If you have non-uniform circular motion, so this is uniform constant velocity, but if this were a track and you're in a car and you started at rest here, then you'd be accelerating, you'd be picking up speed, and you would have, in addition to this centripetal component, you'd have a tangential component as well. But you'd still have this centripetal acceleration component. So yeah, that's where this comes from, just by working through the derivatives. And let's see what else we can get out of this. So you can never, you don't even have to memorize this, because you see what we did. We just started with this expression here, And that is literally written, you know, off of the board here. Of course, we're letting this angle be omega t, which just means it's growing uniformly in time. So you don't have to even memorize these. If you memorize one of these, but you already know this one, just take the derivatives and see what happens. Okay, so what else happens that I wanted to get to is the relation of these, if I can erase this, quantities to each other. We have enough there on the left. So we have V equals omega squared R, and the magnitude of A not so fast. We have V is omega R, okay? And we have the magnitude of A right here is omega squared R. So this is where we can take the got an omega squared, and we can take the R as being V over omega, and we end up with, I got that backwards, sorry, let's do it right. So we're going to have the omega squared is going to be V over R, the quantity squared times R. So that's the celebrated V squared over R expression that you guys are familiar with as well. Usually in lowercase, I've got the uppercase here right now, but no problem. V squared over R. So that's that centripetal acceleration. I did an alternative derivation of this right at the very beginning of the semester, when we were talking about the shape and size of Earth. So I might, I think I'll return to that one just to drive the point home. Let's see. Yeah, so over here, we can just add to this chart here, and A is equal to B squared over R. Like that, for uniform circular motion. Good. So yeah, just because we can, let me show you this other derivation that we had. So earlier in the semester, this goes all the way back to, I'm talking about the shape and size of Earth, and then I'm talking about the horizontal throw and stuff like that, okay? So I'm just gonna put here earlier, we had these ingredients. We had free fall, and I'm just going to put H equals 1/2 gt squared. Okay. This is right at the very beginning, but we've done a bit of free fall. So that would be just the distance times squared law to release something from rest. Okay. Then the second ingredient here, you'd have the horizontal throw, as I'm going to call it, and this, we've got a picture of us launching with some speed v, I'll call it v naught, from a height h. We get a projectile, we get an arc. And the key here is that if I double this initial speed, it doesn't change the time to fall. And because of that, I can double the initial speed and get out that far. And I can just keep increasing the initial speed until the arc is so flat that it actually matches the curvature of Earth. And if I do that, and if there's no impediments, like an atmosphere, there's no friction, then I actually get a satellite orbit. So V, I'm just right here, V to match Earth's curvature. Okay, Earth's curvature. then we can do this construction here where we imagine we're launching from the surface of Earth or 5 meters above the surface of Earth, doesn't matter, okay? So now we've got the radius of Earth. I'm gonna use lowercase r. We've got this little height h and we've got a distance L, and we're looking at the Pythagorean theorem. So the idea is that I launch with the appropriate speed, but I'm always falling towards the center of Earth. In other words, wherever it is locally down. So that's what I'm actually, the path I'm actually following, and we have r squared plus L squared equals r plus h, quantity squared. So we expand this out, r squared plus 2r, oops, better make up my mind here, and r squared plus 2rh plus h squared. And then we'll drop r squared from both sides, and then we get L is equal to, because I've just got an L squared left, equal to root 2rh plus h squared. And then we're going to do this. We're just going to say v that we're looking for this whole time. We're looking for the actual speed of the orbit is L divided by t. And we'll go under the square root with the t, so we'll have 2r. We're going to have a t squared here, but that h is going to be gt squared over 2. Okay. The h is going to be gt squared divided by 2. This one is going to be gt squared divided by 2 squared 1 over t squared. Is that written clear enough? Can you guys see what happens as t goes to 0? Or as L goes to 0? So now we're taking a limit, and t squareds, the 2's cancel here. Over here though, I've got t to the 4th over t squared. I've got t squared. So when the limit as t goes to 0, this one goes away completely, so I can fill in here. T goes to 0, what's left? Under the square root, right? RG. RG. So that was our derivation of the local or the orbital, of the near Earth orbital speed. Okay. So this was near Earth orbital speed. And if you plug in some numbers, what you'll find is that's just under 8,000 meters per second for a satellite orbit. And you don't have to worry about Newton's law of gravity. Even if it were 100 kilometers or 200 or 300 kilometers, that's still very close to the surface because this is 6,000 kilometers. Okay? So it's not going to change materially. But here, the punchline of this for this class is that what we have is v squared equals rg, or v squared over r is equal to g. But g was just the local acceleration, and this is just a picture on the board. So this is true, generally speaking. If g is the acceleration at whatever distance you are, that's your circular motion, uniform circular motion acceleration expression. Okay. So v squared over r equals a, wherever you are. Okay. So anyway, that brings that together. I brought that up earlier in the semester. This is a nice application here of a number of things. by the way, for the near Earth orbit, this G is just empirically discovered. It's the acceleration you have in this room itself, right? 9.8. Okay, let's see where we're gonna go with this. Let's start introducing. Maybe I can derive the cycloid, yes. Okay, so anyway, here's a new uniform circular motion. What I'll do for a homework, I'm gonna erase this now. So for a good homework problem for this, suppose, I'm gonna use lowercase r. Suppose R uppercase is fine. R cos I'll use an angle phi of t. Sine phi of t. So now we're generalizing a bit. Okay. Instead of this uniform, right? So I'll put as a note here. We had phi of t equals omega t, right? That's what we had before. Now we have phi of t in general. Now calculate v equals v magnitude and a. What happens here is you got a lot of chain rule stuff. So when you take this first derivative, for instance, you're gonna have minus sine phi of t times phi prime of t, right? And so that generates some extra terms that are kind of complicated. We're then gonna find a formalism where when you actually have to do this a lot, we'll systematize it. But for now, this will be a good exercise. Calculate these. And of course, your limiting case, to get back to this, you know, your phi prime of t would be omega, right? And your phi double prime of t, which this thing is going to get you having, you're gonna have some second derivative. What's your phi double prime of t gonna be to get back to this here? Easier. If phi of t is omega t, phi prime is just omega, and phi double prime is 0. Yeah. So that'll show you when you get this complicated formula, you just check those out and you get back to the ones we had before. Okay, so that's good exercise. You do a lot of chain rule from here on out in mechanics. Next semester even more. So now this is the case when I was saying, you know, like you started here at the red light, you got a green light, you start doing your counterclockwise turns, and you got acceleration, so you come to a stop there. Okay, I have enough time to talk about the cycloid. You know what, I can use these. Everybody have this? I'm gonna erase this right here. Good. Okay, there's a really interesting curve called the cycloid. Everybody know the cycloid? Yeah, what is it?
It's like a curve that a point on a circle traces out as it like rolls along.
Like a wheel.
Like a wheel, yeah.
Point on a wheel, yeah. So if you were to put a wheel right here, and take that point, and then roll the wheel forward, you're gonna generate the cycloid. And the cycloid comes up in some interesting applications, okay? So there's an interesting way to generate this without memorizing it. And that is you kind of use a vector property. So the first one, I would have taken a wheel centered on the origin that's rotating clockwise. And I would have x equals, I'll do this next time. I would have x equals r, but since I'm measuring my angle right there, it would actually be negative r sine theta, and y would be equal to r, negative r cos theta. So that would be my first step. And my second step would just be to lift it. Okay. So my second step, I'm gonna lift it, and I'm gonna still have x equals minus r sine theta, but y is now gonna be r minus r cos theta. And my third step, I'm gonna have it roll forward. Okay. So now I'm gonna roll it forward, and rolling it forward is just gonna, in one complete revolution, take it to 2 pi r. So rolling it forward, I'm gonna get x equals r theta minus r sine theta, and y is gonna be r minus r cos theta. So this is a 3-step kind of vector style derivation. Okay. So this first one was just that thing there, and then the second one was I lifted this thing up, and the third one I rolled it forward. So this generates this very interesting curve, and you know, you've seen this if you've ever had a bicycle in your headlights with reflectors on the wheels. Have you ever seen that? At night, like they're going across the cross section and their reflector is going like that. Cycloid. So we're going to, that's a good place to stop. We're going to analyze motion along the cycloids for various reasons. For example, if we now needed motion along this cycloid, we'd have to do just what we did what I just erased. We'd have to make theta a function of t. And then we could have the motion along a cycloid. And what we're also going to do is we're going to invert the cycloid by turning y into negative y, and then that'll be something that, you know, can have oscillations in it, things like that. Okay, good. That's what all we're going to do today. We've got the cycloid, and we're going to start doing, you know, dynamics of motion along systems that can be written like this. This is called a parametrization of a curve. The parameter is theta. Theta runs from 0 to 2 pi. Yeah. So parametrization, we'll leave it with this. Parametrization of the cycloid. Cycloid, got 0 less than or equal to theta, less or equal to pi. Okay, good, that's all we've got.